Now that you've been exposed to the first semester of undergraduate quantum mechanics, it's time to dive into the second semester. Some ideas we'll cover are symmetry and conservation laws, time-independent perturbation theory, the variational principle, scattering theory, time-dependent perturbation theory, adiabatic systems, and some paradoxical interpretations of quantum mechanics. Welcome to Quantum Mechanics 2. Let's start with symmetry and conservation laws. What does this mean? Well, the big idea here is that geometry drives physics. The geometry of a system has an effect on the physics at play. Emmy Noether, a German mathematician, developed a theory to describe this phenomenon. Noether's theorem states that in a system with continuous translational symmetry, linear momentum is conserved. In a system with continuous rotational symmetry, angular momentum is conserved. And in a system with time translational invariance, meaning the system doesn't change if we push it forward in time, the total energy is conserved. Each of these symmetry conservation laws can be represented by an operator. We know symmetry is present if the operator does not affect the Hamiltonian when it is applied. We can also look at the parity operator. This operator, when applied to a function, will change all x to a negative x. A function has even parity if this doesn't change the overall function, and odd parity if it does, by a factor of -1. A system has inversion symmetry if the parity operator doesn't change the Hamiltonian. What does this tell us? Well, this idea can help explain why some transitions between quantum states are forbidden. Looking at the dipole moment vector of an electron, we can use its parity to determine the probability that the electron will move from one particular state to another. Similarly, we can do the same thing with rotational symmetry. This gives us the selection rules. Delta L has to be equal to either positive or -1, and delta M has to be equal to 0, +1, or -1 in order for a transition to occur. In Quantum Mechanics 1, we determined the energy of each state in the hydrogen atom to be 13.6 electron volts divided by the n number of the states squared. This is true at a base level, and for our sake in Quantum Mechanics 1, this worked just fine. But now that we're in Quantum Mechanics 2, we can afford to look a little deeper. Recall the spectrum of sodium, for example, which we know has a thick spectral line in the yellow wavelengths. If we look a little closer, however, this thick line is actually two lines very close together. Thus, we have more states than we thought at first glance, and so we have more possible transitions and energies to consider. Several other factors can affect the energies of each state. First, we have the Bohr energies, which we calculated in the first semester of quantum mechanics. We have the Dirac corrections, which are based on the fine structure, Lamb corrections based on vacuum fluctuations, hyperfine corrections based on the electron spin position relative to the nucleus's spin position, and magnetic field corrections, also known as the Zeeman effect, which basically just says if we're exposed to an external magnetic field, how do we have to alter the energies? Because of all these factors, things get a little more complicated, and so we have to use time-independent perturbation theory. The core idea here is to add a small time-independent perturbation to a Hamiltonian that we already have an answer to. This process allows us to determine the corrections that get us the correct energies. This works great for non-degenerate states, but when the two energies are equal, the wave function components blow up. We thus have to alter our method for degenerate states. We can do so using two main methods, each involving a linear combinations of functions. First is the W matrix method. We can create each entry of our 2x2 W matrix and use ideas from linear algebra to find the eigenvalues of the matrix as well as the respective eigenvectors. The eigenvalues tell us our energy corrections, and the eigenvectors give us the respective coefficients in our linear combination. The second method is the good states theorem. Here, if two states have the same eigenvalue under the Hamiltonian, the states are degenerate, but if they have distinct eigenvectors, they are good states. Here, we can use the energy calculations for non-degenerate states to determine the energy corrections. Now that we understand how these energy corrections work, let's revisit some of the factors we mentioned earlier. For fine structure corrections, the energy correction depends on the J quantum number. We can correct by adding two terms, a relativistic correction to kinetic energy and a magnetic potential energy term due to internal magnetic field. Each of these corrections can be combined to create the fine structure energy correction. Similarly, for hyperfine energy corrections, we will add a small perturbation based on the spin of the electron and the spin of the nucleus. For Zeeman corrections, we add a small perturbation based on the orbital angular momentum and spin angular momentum of the electron, as well as the external magnetic field. The technique we'll discuss is the variational principle. This technique seeks to estimate the ground state energy of an atom without knowing the specific wave function that represents it. This technique provides an overestimation of the ground state energy by using any normalized wave function, and we can then impose an upper bound on this energy to narrow our estimate. The procedure here is to start by picking a trial wave function that contains an adjustable parameter, which we'll call b. We can then use this trial function to calculate the expectation value of the Hamiltonian. Using this, we can find the value of our adjustable parameter b such that the partial derivative of the expectation value of the Hamiltonian with respect to the adjustable parameter is 0, minimizing the expectation value of the Hamiltonian and providing an upper bound on our energy estimate. This technique gives us access to several types of problems. We'll focus on 3. First is the ground state energy of helium, second is the ground state energy of the hydrogen molecular ion, and third is the ground state energy of the hydrogen molecule. In each of these scenarios, we can use the wave function from our solution to the hydrogen atom as our trial function, giving us estimates for each of these energies. Now we'll discuss quantum scattering theory, which we can use for states that have a continuous spectrum instead of a discrete spectrum. Let's start with classical scattering theory. In classical scattering, we can consider hitting a target particle with another particle, sending the second particle moving at a scattering angle theta. In the case of hard sphere elastic scattering, let's consider firing a BB pellet at a bowling ball. With some simple math, we can calculate the scattering angle for the BB pellet. We also have differential scattering, where the greater the vertical distance between the centers of our two objects, the smaller the scattering angle is. Another case is an incident particle beam, where a beam of particles is fired at a target, rather than just firing a single particle. Now that we've briefly looked at some examples of classical scattering, we are ready to dive into quantum scattering. We can use scattering probabilities to divide the target and surrounding areas into 3 regions: the scattering zone, intermediate zone, and the radiation zone. If a particle is in the radiation zone, it will create an outgoing spherical wave. In the intermediate zone, we get an outgoing spherical wave, but this time it's described by a linear combination of Bessel functions, called a Hankel function, where each a sub L is the partial wave amplitude. We can also perform phase shift analysis, where an incoming plane wave will take on a phase shift to create the outgoing wave. These calculations give us the partial wave amplitude and the cross-section, which describes the probability that scattering will occur. Now we can consider using time-dependent perturbations to approximate solutions in quantum mechanics. In this case, we use time-dependent perturbation theory to account for the emission and/or absorption of electromagnetic waves by an atom that transitions from one state to another. This process involves first setting up a 2-level system using the energy of state A and the energy of state B, and then introducing a small time-dependent perturbation to a Hamiltonian we already have a solution to. We can adjust the results from this process to fit a sinusoidal perturbation, as pure electromagnetic waves are sinusoidal in nature. Then we can determine the rate of spontaneous emission. The ratio of stimulated absorption to stimulated emission equals 1, so we can determine the mean lifetime of the excited state by taking the inverse of the rate of spontaneous emission that we calculated. Now let's look at adiabatic systems in quantum mechanics. First, we need to update our definition of adiabatic. In chemistry, this usually means a system where there's no heat transfer, but in quantum mechanics, adiabatic describes a process that occurs slowly. Consider the infinite well problem from Quantum Mechanics 1, with walls at 0 and A. Now consider slowly expanding the second wall out from A to A prime. Since the process is adiabatic, the particle moves from the ground state of the infinite well to the ground state of the expanded infinite well. This change also brings about a change in energy. We've covered many more bases in quantum mechanics now, but what have we really accomplished? Using the information we've learned in both semesters, we can consider interpretations of quantum mechanics. To do so, we'll focus on entangled systems in a variety of contexts. First, let's discuss the EPR paradox, named after Einstein, Podolsky, and Rosen. Consider a 2-particle system where total momentum and relative position commute. Since these particles are entangled, measuring the momentum and position of the first particle automatically tells us the momentum and position of the second particle, without us having to do any actual measurements of the second particle. If you recall from Quantum Mechanics 1, however, quantum mechanics formalism tells us that the momentum and position of particle 2 are incompatible. The Heisenberg uncertainty principle tells us that we cannot know both position and momentum simultaneously. Thus, we have a blatant contradiction, and this paradox tells us that quantum mechanics is incomplete. Similarly, we can look at Bohm's version of the EPR. Here, consider a pion that decays to an electron and a positron in the singlet state. We can thus measure spin angular momentum for the x, y, and z directions for the electron. Each of these is equal to 0. Since the electron and positron are entangled, this tells us the spin angular momentum in all 3 directions for the positron, so we know that its angular momentum in all 3 directions equals 0. Again, looking back to what you learned first semester, quantum mechanics formalism states that spin angular momentum for x, y, and z are incompatible. Thus, quantum mechanics is again incomplete. Another example of this idea is Schrödinger's cat. Let's say we leave a cat in a box with a vial of poison and a particle with a decay probability of 50%. which, if it decays, will break the vial and poison our feline friend. The vial and the particle here are entangled. If we look in the box and see that the cat is dead, we automatically know that the particle must have decayed. Thus, we know what happened to the particle without taking any actual measurements or observations of the particle itself. The last paradox we'll consider is Bell's inequality, which posits that measurements under quantum mechanics formalism differ from those under local hidden variables, where Einstein proposed that particles have definite properties of their own regardless of if we measure them. The inequality states that the sum of the probabilities that two states are the same is greater than or equal to 1. If this is untrue, then quantum mechanics is either non-local and/or non-counterfactual definite. I know things seem a little more complicated than they did first semester, but hopefully the information and tools that you learned in Quantum Mechanics 1 will prepare you well for Quantum Mechanics 2. If you're feeling a little confused, don't worry. You're not alone. In the wise words of Richard Feynman, I think I can safely say that nobody understands quantum mechanics.